there are a few questions that I will be covered today. So maybe first let's take a look at question B. So we are given x1 to x13 and y1 to y16. So yeah, there are specific numbers for the random sample, and also they are sampling from the respective normal distribution. So x1 is coming from mu1 and sigma 1, and y1 to y16 is coming from mu2 and sigma 2. We also have given information that the variance from the first distribution is equal to 1/5 of the second, but the variance is unknown in this case. So we are asked to construct a ratio that follows t distribution with 27 degree of freedom, so another constraint that we need to satisfy. And then using all of the information, consider the distribution x bar minus y bar, and then find a chi-square distribution. Okay, so I think the goal is that we need to construct a t distribution, and the following are just a hint. So we are going to do this in the following way. So this is for question B. First of all, let's find the distribution for x bar minus y bar. So each of the x and y's are coming from normal. So the average of x and y are also coming from normal. And also the difference of the two normals is also coming from normal. So that's the reason why we have this difference falling in normal. And then the mean of this difference of the average is also the difference of the two mean. And if you want to be maybe let me just be more elaborate on this part. So you basically have n copies of mu1, which is to take care of the summation xi. So you have n mu1s, but you also taking the average, which is the 1 over n. So that's why you end up with mu1 here. And then same thing, you have minus mu2. So that will be the underlying reason for why the difference of the average is also the difference of the two means. So that's mu1 minus mu2. And then similarly, you can also expand the variance for the average. And that should give you sigma 1 over 13. So we only have 13 observations, so that's why the denominator is 13. And then similar for the second data set, which is 16. And here we're just going to use a square root to denote the standard deviation. Okay. So this is what we have. And maybe we can also plug in some other information to further elaborate that, which is sigma 2 is equal to, okay, sigma 1 is equal to 1/5 of the sigma 1 square. Okay, which one? Okay, one. So I'm going to write this information here, and then let's plug in. So we can rewrite the variance as sigma 1 multiplied by 1 over 13 plus 5 over 16. Okay. That's one information we can get, or we can talk about, regarding the average, or the difference of the average. And then there's also another equation that we can set up here, which is regarding the ratio of the sample variance over the population variance. So this is going to be a chi-square distribution. I think you probably the professor I think he has already derived this equation here. And we also have another chi-square, and then the sum of different chi-square is also going to be a chi-square, but with the degree of freedom as the sum of the degree of freedom of this individuals. So let me just write it down. So we have this follow a chi-square, and then this following chi-square, and the sum is also going to follow chi-square. And then this is the chi-square degree of freedom 27. So this is coming from, this is a chi-square degree of freedom 12. And this is a chi-square degree of freedom 15. So the sum of that is also going to be a chi-square, but with degree of freedom 12 plus 15, so 27. So these are the two distribution that we can set up so far. Okay, so next we are going to construct a t distribution. So t distribution is going to be a standard normal over chi-square. Let's see. Let's put like arbitrary degree of freedom over its own degree of freedom and then taking the square root. And then you will have a t distribution with that particular degree of freedom. So we are asked to construct a random variable that follow t distribution. And now we have all the necessary component here. We have the normal, and then we can easily change that to a standard normal. We also have this chi-square, and we also know its degree of freedom. So we have all the necessary component here, and that will allows us to construct the t distribution. Okay, so the rest is just we need to plug in to the corresponding position to construct that. So first of all, let's work on the standard normal on the numerator. So here we're given a general normal. We just need to standardize it to convert to a standard normal. And we can convert that in the following way. So x bar minus y bar. This is the random variable that follow a normal. And then we are going to standardize it by minus the mean, which is mu1 minus mu2. So the mean is coming from here. So we are shifting by this amount to centralize the center mass. So after we minus that, we basically moving towards 0. But we also need to standardize the variance. So we need to divide it by its standard deviation. So which is sigma 1 multiplied by 1 over 13 plus 5 over 16. And this is coming from here. And yeah. So because we also have an additional equation here, so we can only express this variance only involving one sigma 1. Okay. So this should give us the standard normal on the numerator. And now we just need to work on the denominator. Okay, so for the chi-square, we just have 12 multiplied by the sample variance for x plus okay, so maybe let me yeah, so I think so here I'm going to simplify this sigma 2 before we talk about denominator. So I'm just going to write this numerator in terms of sigma 1, so that we only have sigma 1 to consider. So sigma 2 squared is 5 multiplied by sigma 1 squared. Okay, so you can see that this expression only involving one sigma square, sigma square 1. And that means we have three copies of sample variance for y. So this is 15 over 3, or over 5. So we only have 3 copies of sy squared here. And then altogether divided by sigma squared, sigma 1 squared. Yeah. So this is the chi-square that we borrowed from here. And the last thing we need to do is just divide it by its degree of freedom, which we already know is 27 by construction, and then taking the square root for the denominator. And now this equation here, which is also a random variable, should follow a t-distribution, degree of freedom 27, following this construction here. Okay, so any question or comments? So let me just summarize what we have been doing in this question. We are given particular numbers of samples for X and another set of samples from another group. They have their own mean and variance. And from there, we can calculate or construct, or we know that the difference of the two average is also following a normal distribution. And then we find out its new mean and the variance, or you can write as the standard deviation. We are also given additional information for this equation here, and then we construct another chi-square distribution by design. Because when we need to construct t, we also need a copy of chi-square, so we need to construct another chi-square here. Okay, after that, we just need to plug into our formula for the t distribution, which is that, and then we just plug in the corresponding component, we have our final answer. Okay. Any question or comments? Okay, next we're going to talk about question C. So derive the distribution for sample mean where they are independent, each of them following gamma distribution, and find the transformation of x bar that follow a chi-square. Okay. This is part C. Okay, so we have x bar is equal to 1 over n summation 1 to, I think it's n copy, right? N copy, okay. xi following a gamma. Let's see. Alpha beta, okay. So we're not only interested in the distribution of x bar, we also need to perform a particular transformation to let it equal to chi-square. So that is something we need to construct. But first of all, let's analyze the distribution for the summation of xi. So you probably have heard this a lot of times. So the sum of a gamma is also a gamma, but we're just going to show it here. And also they are independent. So basically you can just have 1 minus beta multiplied by t, and then alpha, negative alpha, I think yeah. So this is the moment-generating function for a particular xi, not chi, yeah. So this is for a particular xi, but we are talking about the summation. So we have n copy of that. So you also need to multiply, raise to the power of n, and that should give you 1 minus beta t negative n multiplied by alpha. And here we can talk about the x bar by adding additional scalar divided by n here. And this scalar here is only going to affect the t here. So we have this formulation here. And this is just the moment-generating function for x bar. So I think you probably have seen this a lot of time already. Yeah, but what we are interested in is a particular transformation of x bar so that it follows a chi-square. because here x bar is following a gamma distribution. So x bar is following a gamma distribution of n alpha, right? Yes, n alpha and then beta over n. Yes. So x bar is following this particular distribution. But what we are interested in is a chi-square distribution. So we need to perform some transformation there. Okay. And then we are also asked to comment on what is the degree of freedom for our construction. So the construction can be performed in this way by multiplying 2n over beta. So this is actually the answer for this question. And then we just multiply by 2n over beta to x bar. And let's see what this distribution is going to follow. And to verify if that's going to follow a chi-square distribution. So let's denote that as a letter Q. And let's see what is the moment generating function or the distribution for Q. And this is just 2n over beta multiplied by x bar. Okay, yeah. So essentially, this is just another scalar multiplied by x bar. So this is equivalent to the moment generating function of x bar, but with a new t here. So just 2n over beta multiplied by t. And now we can plug in the moment generating function for x bar, and then with this new t here. So that should be 1 minus beta. Beta should be beta over n. So this is the new beta star, and then this is the t star. Okay. So you need to multiply by t star, and then t star is just 2n over beta t. And then the alpha stay the same, which is negative n alpha, n multiplied by alpha. So this is the new alpha star. Okay. So here, this power here is the new alpha star. And then after simplified, let's see, we achieve 1 minus 2, let's see, 2t multiply 1 minus 2t raised to the power of n alpha. And this is the moment generating function for a chi-square distribution with degree of freedom. Okay. We also need to construct here. So we multiply 2 and then n alpha and then divided by 2. Because the moment generating function for chi-square degree of freedom, say, let me use another letter not to confuse here. Maybe say r. This is equal to 1 minus 2t negative r over 2. Okay. So this means we have our chi-square degree of freedom 2n alpha here. So by performing or multiplying this particular ratio in the front to our x bar, we are able to transform this gamma distribution into a chi-square distribution. And then the degree of freedom is, let me rewrite to make it cleaner, to chi-square distribution with degree of freedom 2n alpha. Okay. Yeah, so any question or comments? Yeah. Yeah, because here it's just negative n alpha. So let me, so you can, okay. So let me comment on, so your question is regarding why there's the 2, what the,
It's just because you divided by 2, so you have to.
yes, because the original, so starting from this line here, it's 1 minus, so beta and beta cancel out, n and n cancel out. This is just 1 minus 2t negative n alpha. But here I'm just multiply by 2 and then divided by 2, so it still stay the same. But we need this 1 over 2 here because we want to match the homogeneous function. So after you have a 2, so whatever on the numerator is going to be your degree of freedom, which is 2n alpha. Yeah. Yeah, good question. Any other question or comments? Yeah.
And the negative sign still supposed to be there on the final
Yes.
distribution? So like to the negative 2n alpha.
Oh, you mean here? Yeah,
Yeah.
there's a, yeah, thanks. Yeah.
Okay.
There's a negative sign. Yeah. Sorry. Yeah. Thanks. Yeah. So the solution to the question, just for the answering for this question, the transformation is that multiply by 2n over beta. So that should be the solution. But the reason that it's just here that we show that as following chi-square, and then with this new degree of freedom. Yeah. Okay, next let's talk about. We have lots of time. Good. Then maybe we can talk about question E. Yeah, so we just have a t distribution, degree of freedom n, and then find its mean and variance. Question E. So we are interested in a random variable x and then the variance of x, where x following a t distribution, degree of freedom n. So we can solve this by using the definition for t distribution. So again, t is standard normal over chi-square, degree of freedom n. So it should have the same degree of freedom here, divided by n. Okay, so we're going to use this particular construction. Okay, so we are interested in E of this. Or the expectation of this. So just to be more explicit, this is 0, 1, and then chi-square is just. So this is just a notation for random variable, not the. Yeah, so sometimes the notation might be, or the notation might be abused, but this is just referring the random variable that follow a chi-square. So yeah, okay. And that is just a chi-square degree of freedom n. And we have maybe the expectation square root of n and then z multiplied by chi-square and then raised to the power of I think it's negative 1 over 2, right? Square root. Okay, yes. Yep. Okay, and another thing we need to mention is that they are independent for the numerator and the denominator. Otherwise, this definition of a t distribution is not valid. So that gives us that z is independent of this chi-square degree of freedom n here. So with that another information here, we are able to decompose this expectation to products. So square root of n as a constant. Expectation of z. Expectation of chi-square. And degree of freedom n, but don't forget raised to the power of 1 over 2. And then the reason why you can decompose, okay, maybe let me write it here, is because z and the chi-square are independent. That's why you can write it as a product. And this independence is coming from the definition of the t distribution. Okay, and then next, I think, yeah, you don't need to, because the standard normal has a mean of 0, so everything is just 0. Okay. So the expectation of a random variable that follow a t distribution with arbitrary degree of freedom should have a expectation of 0. And the reason is that the 0 is coming from the expectation of the standard normal. Any question up to this point? Okay, next let's talk about the variance of this. Z over chi square degree of freedom n divided by n over square root. So we are going to write this as the expectation of the second moment of the entire thing. Right. And then minus the square of the first moment. But we have shown earlier here, this is 0, so you just have minus 0. Okay. Again, independency. I think this is n, right? And expectation of z squared. So the second moment of a standard normal. And then the expectation of chi square n. Right. I think there's a inverse or a raised to the power of -1, right? Yes, everything here raised to the power of -1, closing the expectation. Okay. And let's further elaborate that. The square of the second moment is equal to the variance plus the mean of the first, the square of the first moment, which is just the mean. And yeah, z is normal, so actually this is just 1 plus 0 squared. Okay. But I'm just going to use arbitrary notation here. The key thing is that we need to find the expectation of a chi-square distribution that raised to the power of -1. And also chi-square is just a special case of a gamma. So we have this, or following a chi-square gamma distribution with degree of with the alpha n over 2 and then 2. Once we have the gamma, we can have expectation of say u raised to the power of k. Let me just make it more general. So u, and let's say this is just u, a gamma a chi-square distribution. So any gamma distribution is raised to the power of particular k, and then we want to evaluate the expectation, we can just use the formula here, which is the alpha minus 1 beta k, and the alpha, a gamma function of alpha. Right? Can someone, does someone remember is this the formula? Did I write it correctly? Just copy paste from the formula that you get in your previous handout or homework. I think this is the one, yeah. And now we just need to plug in the terms. So yeah, so this formula is that what we derived in homework 1, I think, all the way, yeah. So alpha here is n over 2 minus 1, beta is 2, and k is -1. So let's write down k is -1 here, over gamma function of n over 2. Okay, and let's further simplify that. It's just 1 over 2, and then gamma function of n over 2 minus 1, and then n minus 2 minus n over 2 minus 1 multiplied by that. Okay, so there's just another property that we apply to the gamma function, and that should cancel out or give us the final terms, which is, yes, n over 2 minus 1 this is in the denominator, right? So -1. Let's see. Can I make yeah, because this notation look ugly, so let's further. Oh, okay. One way you can write is n minus 1 over n minus 2. Okay. And this should give you one over n minus 2. Okay, so I think this form is simpler. Yeah. So what I did is just first elaborate that as n minus 2 over 2, and then taking the inverse, and then 2 and then cancel out with this 2, so you should have that. Okay, so here we have this multiplied by 1 over n minus 2. And that should give you n over n minus 2. Okay, because this is just 1, and then n over n minus 2. Okay, any question or comments? Yeah, I think lots of things here. It just once you've set up the equation or the formula, the rest it just plug in the terms to the correct position and then simplify, or using some of the tricks that you use or that you derive in the previous homework. So yeah, more of algebraically many operations, but there's nothing nothing fancy going on. Yeah. Any question or comments? Okay. Next, let's talk about question F. So lots of things is similar here, because actually F distribution is just another transformation from the T distribution. So you will see lots of similar procedures here. Question F, we have our F distribution follow N and M. Okay. We want the expectation of this of this and the variance of this random variable N M. And similarly, we are going to solve this problem from its definition. From its definition. Yeah. And the definition for F distribution is chi-square, degree of freedom n over degree of freedom, and then a chi-square, degree of freedom m over degree of freedom. So that is just a definition for the F random variable that follow F distribution. So again, plug in this ratio here. Okay, so maybe I just not to skip any chi-square m over m. Let's move the constant. Let's see which one is easier. Okay, so let's move the constant outside first. So n over m, m over n, which is this m here from the denominator over the one in the over the denominator in the numerator. Yeah, and also this is independent. Okay. So we can write it as a product multiplied by the expectation of a chi-square, and there's a power raised to -1 here. And let's see. So maybe let's work on the first expectation here. So chi-square degree of freedom n is going to be a gamma degree of freedom n over n over 2 beta 2. And then the expectation of a gamma distribution is just alpha beta. And then it's just n over 2 multiplied by 2 equal to n. So we have that the first expectation is equal to n. Okay. And then for the second expectation here, we just need to use the formula again because we have a power with k -1. So we need to apply the formula. So that should be, let's see, let me just revisit. Yeah, so let's just copy it down. Okay, so I think this is exactly the same. It's just the n is m here. So here I'm just going to write 1 over m minus, is it m minus 1 or m minus 2? Oh, m minus 2, okay. Yeah. So it is the same derivation from the previous question. It just, we changed the degree of freedom from n to m. And that should give us m over m minus 2. Okay, so I think that should be it. So this is chi-square. With that, yes. Oh, let me just double check. Yeah. M over 2 over 2, and then all the things here. M minus 2, m minus 2. Okay. Yes. So I think that should be it. Yeah. Yes, okay. And next, we also need to evaluate the variance here. So, yeah, because I don't have the solution, so I'm just deriving from scratch. So let me know if you see any typo. So again, we have this ratio here. This should be the expectation of m square over n square chi-square of n raised to the power of 2, and then chi-square of m raised to the power of -2. Closing that, minus the square of the first moment, which is m over m minus 2 square from the first part. Okay, so now let's just analyze the first expectation. So m square over n square, expectation of chi-square, and then raised to the power of 2. So here, just make sure that you don't make this as a power of 4. This is just referring to, this is just a notation for chi-square that it has a 2 here. But these are totally two different things, so don't make it a power of 4, okay? And then this is chi-square, degree of freedom m raised to the power of -2. Closing that, m over m minus 2 squared. Okay, so I think everything is just the same. You need to use n over 2 minus 1 and 2 raised to the power of k, which is 2 in this case. And then this is a gamma function, okay. And then a gamma function of n over 2 minus 1. Okay. And then multiply by a gamma function of m over 2 minus 1. And then 2 raised to the power of negative 2. Gamma function of m over 2 minus 1 minus m over m minus 2 multiplied by taking the square. Okay, let's see. Can we simplify? I think this is just coming from here, m minus 2, n so we have a 2 square here, and then let me just double check. So we are going to use that, and then these two cancel out, so we should have 1 in the denominator. Okay. So n minus 2 over 2 raised to the power of negative 1. And here m minus 2 over 2 raised to the power of negative 1, but the 2 here is raised to the power of negative 2, and then minus m over m minus 2 squared. Okay, because I don't have the solution, so before we proceed, let me just double check in case I have any typo. We have that, and that. These two should be cancelled out. We have that, and then n minus 2 over 2 inverse. Okay. N minus 2 over 2 inverse, n minus 2 over 2 inverse, and then 2 raised to the power of negative 2 minus that, and then that. Okay, so I think any typo? Yeah.
For the gamma function, should the denominator be just gamma n over 2?
Which part? Which one? This one. And then in the denominator.
Should it just be like m over 2 instead of the minus 1?
Because using the
Yes. Perfect. Yeah. Yeah. So yeah, this is before applying the formula. Yes. So yeah, before applying the formula. Yes. Is this what you mean?
Yeah.
Yes. Yeah. And after applying the formula, we minus a 1 and then bring the yeah. Thanks. Perfect. Yes. But any error here? I think because I'm doing it from scratch, so anyone think if there's any typo in this line? Should be okay, right? Yeah. Okay, yeah, thanks. And then let's see, this 2 and this 2 can be cancelled out. M squared over n squared. N minus 2 over 2 over that, and then m minus 2 over that. Okay, yes, I think that should be 4m squared over n squared multiplied by n over 2 m over 2 m minus 2. Okay, if anything, if all the algebras are correct, then this should be your answer. Okay, yeah. Any question or comments? Okay, I think that's not yet. I forget to minus this thing here. Minus m square m minus 2. But I don't think there's an easy way to simplify this. Okay, so I think I will leave it as this form for final answer. But if you want, you can do n square n minus 2, m minus 2, and then m minus 2 square, and then aggregating all the numerators if you want. Yeah, but I think I'm just going to leave it as this form here. But I think the algebras should check out. Yeah. Yeah, so we only have 6 minutes, so okay, just let me comment about maybe part J. So I and J is asked to find the mean and the variance for non-central T and non-central F. So the methods or the procedures should be the same, except that for the non-central F or the non-central chi-square that you use, and then with non-central, this is just one additional comment that you might use. So for non-central parameter theta for a chi-square of that, let's denote this as u, and then the moment-generating function for a non-central chi-square has the form of 1 minus 2t n over 2, but multiplied by the exponential of theta multiplied by t over 1 minus 2t. Yeah, so you might need to use this to take the derivative with respect to t and then set t equal to 0 to find the expectation of u when you evaluate the expectation of a non-central f, where non-central f with a non-central parameter theta is just chi-square n ncp theta over n with a chi-square m over degree of freedom m. Yeah. So when you find the expectation of this, you might need to find the expectation of the chi-square. But this is not just the Euro chi-square or the gamma distribution that we see earlier. This is the non-central version. So the moment-generating function is going to be like that. And then if you need to find the the expectation, take the derivative, evaluate t equal to 0, you will get the expectation. So that's the only thing that you might need, this additional information from the moment-generating function that could help you to find the expectation. Okay, so I will stop here. This is for part question J, I think.